The purpose is for us is to find a method how to design the rail profiles for the grinding purpose, because a lot of paper has been talking about how to grinding the rails, but how about the target of the rail, how to design it? Is there any the efficient method? How to press this one? No response. Which one? Okay, oh, okay. So we are talking about first is the research background, and then is how to design the rail profiles. And then we have the test field, and to verify it's a method. Oh. Doesn't work. Which one? Oh, this one. Okay. Now this slide, we can see the wear of the profiles is very sad. But so we have as a way to grinding, to recover the wear profiles. There are several categories. Here I didn't spend time on that. And then with the ways to deal with the wear, how to selecting the grinding profile. Now we have the traditional way. We have a template. Several times we have 3 or 5 templates by the experience. This is the way. Then we must find the other ways. But all above this method have some defects. And this is our method. And this is a demand for the grinding. This is why you're grinding. And then according to this demand, we can get the data of the wheel profiles. And then we can measure the rail profiles, especially on cubes. They have the different profiles. And then we can modify a proper loading radius differences. And this function will have some key parameter. Maybe one is the equivalent conicity. This is for the stability. And also for the curving ability, the loading radius differences. And we can modify that. And then we can estimation assistant bound graph. Yeah, the bound graph is contact zone, contact point and contact width area. And then finally, we can work out the feasible solution and constraint the condition is similar. And then establish the feasible solution base. And then select a feasible solution result. So this is measured by the program. This is a program. And the output of the program is a rail profile. If this rail profile satisfies the demand, how to do it? We can buy the simulation, computer simulation with the vehicles and with the truck, and also by the stress calculation of the contact areas. If it's okay, then we can for the application for the grinding. If it's no, we have to reduce. We have to go back to do again and again. But this process is faster, and this is the mathematical models how to calculate out the rail profiles. So you can see this is a wheel and this is a pair of rails, and this can be different. Left one and the right one can be asymmetrical. And this is the equation of this wheel and the rails, and this is a condition of the contact, condition constraint here. Now it is an example of the calculation. This is the actual measured wheel and the rail. So you can, this is the high rail, this is a low rail, and this is a contactor condition. So we can find by this RRDF, this contact is not good because there are less rolling contact radius on cubes when the wave set moves. So we can modify that. So the red one is a target RRDF we modified by the manually. So we have the larger one. And then we got to the new rail profiles. This is high rail. This is for the low rail. So the red one is the new profile. And then we do the calculation again with the same wheel set. So we can find that these improvements has been done by this new rail. Now we have the tester. We did many tests. This is one of these tests. So you can see this is a rail on the cubes. The radius is 300 meter. And this is the design of the grinding rail profile. And this is a comparison before grinding and after grinding as a wear rate changed. So this is before grinding. This is after the grinding. This side, this is top wear. They also changed. So we can extend the rail life by the grinding with the properly designed rail profiles. Okay, and now we have conclusions. A rail profile design method for the grinding rails at the cube is presented and based on actual wheel rail profile measurements and the optimization function of loading radius differences. All of the results prove that the optimized wheel profile effectively improves the geometrical relationship between the wheels and the rails. The third one is actual implementation has been carried out in the grinding of track line, and the theoretical analysis results are in good consistency with the field test results. And the program running, the time consumed for the program is faster, maybe just several minutes. So we can go to the new rail profile. And this new rail profile can be asymmetrical. Can be asymmetrical. Okay, thank you very much. So I save time. Any question?